Hello, today we are going to mention the addition formulas on elliptic curves, and this is typical elliptic curve of Weierstrass form. I'm going to pick two random points on this curve. Let's say P and Q, and these are the coordinates for these points. I'm going to draw a linear line which satisfies these 2 points, and this line intersect the curve on a new point. And let's say it minus r. I call it minus r because addition formula proposed to finding the symmetric point of this minus r point. And this is the addition point of P and Q. This curve is symmetric about x-axis. That's why x coordinates of r and minus r points are same, whereas its y coordinates absolute values are same. We also know that blue linear line satisfies this equation. Y is equal to beta times x plus mu. Here points P, Q and minus R on the blue line. This means that they must satisfy this equation. I'm putting coordinates of P to this linear equation. And y1 is equal to beta times x1 plus mu. Similarly, I'm putting coordinates of minus r because it's on this line too. And its y coordinate minus y3 is equal to beta times plus x3 plus mu. In the first term, I'm getting the exact value of mu, and it's equal to y1 minus beta times x1. And I'm putting this mu value in the second term, and this becomes minus y3 is equal to beta times x3 plus in the parentheses y1 minus beta times x1. And I'm opening the parentheses, and this is the final form of this equation. As seen, both beta times x3 and beta times x1 has a beta multiplier. That's why I'm putting beta as the common multiplier. And y3 is equal to beta times x1 minus x3, and out of the parentheses minus y1. And this is the value of y3. I can find the y3 point based on x1 and x3 and also beta. But beta and x3 values are unknown from now, and I'm going to find these values. Remember that I have this red curve. This satisfies this equation. Y squared is equal to x to the power of 3 plus a times x plus b, and this blue line. Let's combine them. I'm going to put this term beta times x plus mu instead of y in the first term. Beta times x plus mu's squared value is equal to x to the power of 3 plus ax plus b. And I'm opening this parenthesis. First term's squared value plus second term's squared value and plus 2 times first term and second term, and this becomes beta squared x squared, that's the squared value of the first value, plus mu squared is the squared value of the second value, and 2 times beta mu x is equal to x to the power of 3 plus ax plus b. Here I'm putting all terms on the same side, and x to the power of 3 minus beta squared x squared plus ax minus 2 times beta mu x plus b minus mu squared is equal to 0. Both ax and minus 2 beta mu x terms have x multiplier. That's why I'm putting x common multiplier, and beta minus mu squared values are constants. They don't have a multiplier, x multiplier. Here we are going to consume a polynomial relation rule, and states that sum of the roots have to be equal to negative coefficient of x squared. Let's prove it. We have already known that this is the our elliptic curves equation, and it has to have three distinct roots because it's a cubic equation. I mean that you can see this value. Let's say its roots a, b, and c, and I can express this equation as x minus a, x minus b, x minus c. Let's multiply first and second parentheses first. I mean that. Also, this becomes x squared minus bx minus ax minus a times b times x minus c is equal to 0. Let's multiply this two parentheses now, and this is the final form of the this equation. It's complex, I know that, but as seen, this and these terms have x squared multiplier, and I can combine them as seen. I can ignore other terms. As seen, minus in the parentheses a plus b plus c. These are the three distinct roots of the cubic equation, and I can say sum of the roots, I mean that a plus b plus c have to be equal to negative coefficient of x squared, as seen. We can prove it. Let's turn back. I can apply a polynomial relation rule here, and it states that sum of the roots have to be equal to negative coefficient of x squared, and here negative coefficient is minus b squared, 2 times minus, because minus b squared is the coefficient of x squared, and it has to be equal to sum of the roots. Sum of the roots sum of roots are x1 plus x2 plus x3 as seen. And I can reflect the sign into the parentheses, and it becomes beta squared is equal to x1 plus x2 plus x3. And I will move x1 and x2 terms on the left side, and then it becomes x3 is equal to beta squared minus x1 minus x2. You might remember that in the previous slides I have calculated the y3 value, and it also have beta term, and beta is still unknown for me. Let's calculate it. Let's mention the blue line and the known points on the curve. I can find the beta as slope as tangent alpha, and it's equal to y2 minus y1 over x2 minus x1, because you might know that that's the tangent value. But P and Q are different points in this case. What if they are equal to each other? I mean that P plus P. In this case, x2 and x1 values are equal to each other, and this becomes undefined. That's why I need to define another rule for doubling a point. If P is the point I would like to double, then I will create a tangent line here. And this tangent line intersects the curve on a new second point, and I will call this minus 2p. And it's symmetric about x-axis will become my doubling point. And I can calculate this by finding the derivative. This is the equation of the curve, and I find its derivative value 2 times derivative of y is equal to 3 times x squared. This should be x squared plus b times dx, and dy or dx is equal to 3 times x squared plus a over 2y, and that's the actually beta value. Now I have calculated the beta x3 and y3 values listing for doubling. To sum up, I need to find the beta value first, and if they are equal to each other, p and q values, then I need to use this formula. On the other hand, p and q are different points. I need to find the slope formula. Then these are the calculations for the new point x3 and y3. Thank you for watching, and see you next time.